Chapter 3, all about vectors. A vector is defined as a mathematical quantity with magnitude and direction. We've seen some examples of vectors already, things like velocity and acceleration are two good examples of vectors. When you see these written in your book, a velocity or an acceleration, to describe them as a vector, they'll either be in bold, or occasionally you might see a little variable v for velocity with a little arrow over it. That little arrow right there, that means I'm talking about a vector. And I will likely switch between these different orientations. So I might bold some things, I might put things in little arrows. If bolding is too difficult, you should understand these arrows mean I'm talking about a vector. One of the first vectors that your book discusses is the so-called displacement vector. This is kind of a strange concept for some students, but we'll go ahead and cover it. Displacement vector. I want to go from point A to point B. The shortest distance between those 2 points is a straight line. I put a little arrow on it. This is my displacement vector. And this displacement vector only cares about the final position, xb, relative to where I start, xa. It doesn't care about the path I take, so I could curve up and then back down. My displacement is always going to be xb minus xa. This is often confused with the scalar quantity known as distance. And there's one example that I can think of that really makes these differences very, very clear. That example that demonstrates the displacement vector versus the distance scalar is throwing a ball up in the air. Say I take a ball, I throw it up. I throw it up a distance of 1 meter, and then it falls back down a distance of 1 meter to where it started from. If I discuss my distance has no idea what's going up, what's going down. All it cares about are the numbers, the magnitudes of how far I went. So my total distance that I travel in throwing this ball up is 2 meters. Most students would venture to say that the displacement, how far this ball traveled, is also 2 meters. This would be wrong based on the definition of displacement. Remember, displacement only cares about the final position, in this case, where I am right here, minus my initial position, again, where I am right here. And if you notice, the ball kind of lands at the same height that I threw it from. So in this case, we have some height that we're doing. So I'll put my coordinate axis in here. I have my x and I have my y. So I'm traveling in the y direction. So I'll say I have some final height yb and some initial height ya. And the difference between those two is going to be my displacement. And if my ball lands up the exact same place where I threw it from, then these distances cancel out. And I get a total displacement of 0. I ended up where I started. This is the common confusion that you get between distance and displacement. Distance describes how far you go. Displacement describes how far you go relative to some initial starting position. So it is a vector quantity. It cares about where you start, whereas displacement doesn't. It cares about how big your distances are. Your book discusses various ways to add vectors. I won't go too in deep depth with this. We'll just summarize. We have a C vector. Remember, this little arrow that you see will sometimes be used to represent a vector. Some C vector is equal to an A vector plus a B vector. We can add these algebraically, or we can add them graphically. So with graphs, what we want to do is add using an approach called the tip to tail. Tip to tail. So then we draw a coordinate axis. I have x, I have y. Let me draw a vector A. Okay, I'm going to reach the tip of this vector A, and at that tip I'm going to draw my vector B. Okay, so I have an A vector and I have a B vector. I use the tip to tail method. I take the tip of vector A and stick the tail of vector B on that, draw my vector B, and I end up with some final vector, some resulting vector, that is the combination of those two. That's going to be my resultant vector C from adding my vectors together in the tip to tail method. Other interesting things about vectors: the order doesn't matter. Order does not matter. I can take my same coordinate system, my x-axis and my y-axis, and I could add my vectors b plus a. So I take my b vector, put it at my origin, I draw my b vector in, same length as the vector above, and then I can draw in my a vector, and the resultant vector c is still about the same, the same length. So what this means, this is a commutative law of addition. That means vector a plus vector b is equal to vector b plus vector a. And the final useful vector addition characteristic that I'll mention is that the magnitude of the resultant vector, so the magnitude of C, the vector that results from adding together vector A and B, is less than or equal to the magnitude of the individual vectors added together. Just to help us out, clarify these little bars, which usually mean absolute value. In physics and math, they are often taken to mean a magnitude. So the magnitude of a vector is less than or equal to the sum of its parts. One little point to note about subtracting vectors: you do it the same way that you add a vector, except you add a negative vector. So you just flip the sign. By flipping the sign, you're changing the direction. The easiest way to conceptualize this is think of your motion sensor. Think of moving towards or away from your motion sensor in your labs. When you're moving towards, your velocity was a certain sign. When you're moving away, towards or away from the motion sensors. Flip the direction, you flip the sign. So you can add a negative vector to subtract it. So one of the most useful skills that you can develop in working with vectors is to break them up into their components. So this is going to require trigonometry. So let's draw a vector. We'll call this vector r. And this vector r has a little piece that's going in the x direction. So we'll draw a little piece of r that's going in the x direction. I'll call that position vector x. And we have a little piece going in the y direction, going up. That's going in the y direction. So I can take these two vectors, x and y, and I can add them tip to tail. So I take the tip of my vector x, attach the tail of vector y, add it together, and I get my vector r. These vectors, this vector r has an angle of theta, and I can use this picture to tell me everything I want to know about the components of a vector. If I notice, that's a right angle. So this is a right triangle. So that means we need to use trig. So let's start writing down some quantities of interest. Let's write down the cosine of theta. cosine of the angle in this triangle. Cosine of theta is equal to the adjacent side, x, over the hypotenuse, r. Cosine theta equals x divided by r. So this means that my x component, if I solve for x, is going to be equal to r times cosine of theta. And I just found the x component of my vector. I can use a similar approach to find the y component. I can find sine of theta. Sine of theta is opposite side. It's going to be y over hypotenuse, which is r. So sine of theta is y divided by r. I can solve this for my y component. Y is equal to r times sine of theta. I can use Pythagorean theorem. I can find what r is equal to. R is equal to the square root of x squared plus y squared. Pythagorean theorem for a right triangle. And the final piece of trig that we would want to know, tangent of theta is equal to the opposite side over the adjacent side. So it's going to be equal to y over x for this particular case. These are the four kinds of things that you'll need to be able to do to find the components of any vector. So the general situation we'll have for most vectors is this picture over here. We'll have an x-axis, we'll have a y-axis, we'll have some vector, and we'll have an angle that's relative to the x-axis. So if this is the case, then in general, we'll have our vector A. We'll have some x piece of our vector A. That x piece is going to be a times cosine of theta. We'll have the y piece of our vector A. It's going to be a sine theta. And then we can find the magnitude of our vector A. Remember, these two little bars that specifies magnitude is equal to the square root of ax squared plus ay squared, which is just the Pythagorean theorem. Now, an important point to make about these general rules is that they are general. You could have a case something like this, where the general rules don't actually apply. So I still have my vector A. Here's my vector A. I can write down my vector A. If I want to write down AX, I need to look at where AX is. A along the x-axis. A parallel to the x-axis. This is going to be my AX. Generally, we would put a cosine theta. We can see AX is on the opposite side from my theta. The opposite side comes into the sine of the angle. So this case, AX would be a times sine of theta. AY, y side, let's draw it in. Our AY component of our vector, and we can very clearly see that AY is adjacent to my theta. The adjacent trig function is going to be cosine. So AY in this case is a times cosine of theta. And the magnitude of A is still going to come from Pythagorean theorem, still going to be ax squared plus ay squared. So this is a caveat that your book doesn't mention too well, but you should always look at where this angle is. The general rules might not always apply. You can't just memorize AX is a cosine theta. You have to look at the picture in every case. So now that we know how to find components of a vector, we can talk about how to add vectors and how to do it without making graphs. So let's say I have a vector C that's equal to the sum of vector A and vector B. We have a property of vectors that tells us that the magnitude of that sum vector, the magnitude of C, is going to be less than or equal to the magnitude of A plus the magnitude of B. So a vector is less than the sum of its parts. And the reason for this is that when adding vectors, you can only add components that are in the same direction. And let's flip to see an example. So this is the situation that we're talking about. I have a vector c. That vector c is the addition of a vector a plus a vector b. We've seen that I've done the tip-to-tail method to add my vector a to my vector b, and I've got a graph that shows me my answer. But what if I don't have that graph? What if I don't want to graph the answer? Then I have to add these components of a and b according to the directions that they're going in. I have my coordinate axis, my x and my y. So I have to break my vectors into their components. I have some vector ax, some little bit of a that is going in the x direction, and I have some little bit of b that's going in the x direction. I also have some little bit of a that's going in the y direction. Likewise, I have some little bit of b that's going in the y direction. And to get the final answer here, I need to add the like directions. So to get c going in the x direction, it's going to be equal to ax plus bx. And that will give me my cx, which I can draw in right here. To get my cy, I'm going to need to add ay plus by. And there's something to note here. If we notice, vector ay is going up. In chapter 2, I mentioned that I like to choose my coordinate system in such a way that I draw my coordinates, and I choose anything that's going up as positive, anything that's going down is negative, anything that's going right is positive, anything that's going left is negative. So if I look at my vectors here, my ay is going up. I chose anything going up is positive, so ay is going to be positive. Then I look at by. by is actually negative. It's going down, so it must be negative. So I need to plug in that negative for my by. So my cy is the sum of components in the y direction. Then if I want to know the magnitude of c, how big c actually is, I can do c still going to be the square root of the vector components of c. c in the x direction squared plus c in the y direction squared, and take the square root of all of that. And we can extend these rules into 3 dimensions. So we have a cx is equal to ax plus bx from last slide. We can also do cy is equal to ay plus by. If we have a third dimension, typically we choose the z direction, so cz is going to be az plus bz. And then finally, the magnitude of our vector c is going to be equal to the square root of cx squared plus cy squared plus cz squared. So this would be the most general case for how to add vectors if you have them operating in 3 dimensions, both the x direction, y direction, and the z direction. In fact, we use 3D motion so much. For 3D motion, we've defined something. We've defined something called a unit vector. In this case, the word unit means magnitude of 1. So unit vectors are some kind of vector that have a magnitude equal to 1. So they're only used really to describe direction. since they have a magnitude of 1, they don't change the magnitude of whatever vector, whatever quantity you put them with. For the x direction, our unit vector is called I, which you might kind of see me write a little bit differently as equal to I with a little hat, with a little arrow over it. These mean the same thing. Y has a unit vector that your book calls J. You might see me again write this with a J with a little arrow over it. We call it J hat. And then Z direction, we have the vector, the unit vector K, which again I might write sometimes as K hat. These are all unit vectors. They move in whichever direction they're associated with. So I is in the X, J is in the Y, K is in the Z. They all have magnitude equal to 1. You can often see vectors written as the A vector is equal to the magnitude of A in the X direction. Notice no little arrow, so I attach this little I hat to tell me the direction, to attach on the vector characteristic of direction, plus AY, the magnitude of my vector in the Y direction, and I'll attach a little J hat to tell me that it's moving in the Y direction, plus AZ and a little K hat to tell me that I'm moving in the K direction, the Z direction. To get some practice with these unit vectors, I suggest you try checkup 3.3. Now we know how to add vectors, we know how to multiply, subtract vectors. Now we need to figure out how to multiply them. There are two ways to do this. We have something called a dot or scalar product. So if we take a vector, vector A, and dot it with the vector B, this dot has a very specific definition. A dot B is equal to A times B times cosine of phi, where phi is the angle between A and B. So what does that look like? Say I have two vectors. Here's my x direction, here's my y direction. I have my vector A, I have my vector B. And they're separated by some angle phi. So I can multiply these together in a dot product, and A dot B is going to be A times B times cosine of phi, the angle that separates the two. One of the most useful aspects of the dot product comes when we take two vectors. Let's say we have a unit vector in the x direction. Remember, that's going to be I hat. If we have a unit vector in the y direction, that's going to be j hat. And let's say I take the dot product of those two vectors, I dot j. Seems like it's going to be complicated. I magnitude times j magnitude times cosine of the angle between the two. The angle between these two is 90. Cosine of 90. The magnitude of I is 1. The magnitude of j is 1. So I dot j is equal to 1 times 1 times cosine of 90. Cosine of 90 is 0. So I dot j is equal to 0. The useful aspect of this, what this means for us, is that any perpendicular vectors have a dot product that's 0. Have a 0 dot product. So here we have an example so we can understand what the dot product is actually doing for us. We have our x-axis, we have our y-axis, we have vectors drawn. I have a vector A that's entirely along the x-axis and a vector B that's acting at some angle theta. I can take the dot product of these. A dotted into B is equal to the magnitude of A times the magnitude of B times cosine of theta. If I look at the second part of this, b cosine theta, that should look very familiar. If we remember our components, that's simply bx. And we can see the magic of the dot product. The dot product takes a vector, vector A that's going in one direction, multiplies it by a second vector, but only picks out a certain amount of that second vector. It picks the amount of the second vector that goes in the same direction as the first vector. That's where this b cosine theta comes in, specifically this cosine of theta. It selects out only the part of the second vector that goes in the same direction as the first vector. This is a simplified example where we have something going entirely in the x and entirely in the y direction, but it works for anything. It would work for two vectors at angles. I could have a vector A, I could have a vector B, I could take their cross product, and this would select out the amount of vector B that was going in the same direction as vector A. The final point to discuss in this chapter is the cross or vector product. Let's say I have two vectors A and a vector B. I can find their cross product C is equal to A crossed into B. Mathematically, the magnitude of C, remember these little bars, again, magnitude, is equal to the magnitude of A times the magnitude of B times the sine of the angle between them. But here we have a difference from the dot product. First, we have the sine of the angle. So perpendicular vectors are no longer zero. Second, this is called a vector product. A vector has magnitude and direction, so we need to find the direction of C as well. With the scalar product, we didn't have to worry about that. We can just multiply our vectors together, multiply their magnitudes, and we get a magnitude. We're happy. With the cross product, we need a direction, and that direction is going to come from the right-hand rule. This can't really be described very easily through a video. So what we're going to do, we're going to talk about this in class, and I encourage you to read page 84 and 85. If you don't understand, then ask questions. If you do not ask questions, I guarantee you a right-hand rule question will appear on your quiz. Now there's shortcuts that we can follow, there's the right-hand rule we can follow, but sometimes we have to find the cross product mathematically, and we can do this by expanding out these vectors. So this vector A is really talking about AX, some amount of A going in the X direction. So we're going to specify that with I hat, plus AY, which is going in the J hat, plus AZ, which is going in the K hat direction. So that's my vector A completely expanded out. And I'm going to cross that into my vector B. BX in the I hat direction, plus BY in the J hat direction, plus BZ in the K hat direction. So I've written my vectors out as detailed as I possibly can, and I need to take the cross product of these two. I can look at a couple little shortcuts. A nice little shortcut. A cross B is A times B times the sine of the angle between the two. Sine. When is sine 0? Sine of theta equals 0 if theta is equal to 0. So what that means is any common directions for two vectors are going to give me 0 in the cross product. So AX times BX is going to be 0. AY times BY is 0. AZ times BZ is 0. And there's a shortcut. There's a way to figure this out using matrices. So all I've done here is rewritten my A cross B in the form of a matrix. So I have the I hat direction. What do I have operating the I hat direction? I have AX plus BX. I have my J hat direction, AY plus BY. I have my K hat direction, AZ plus BZ. This is the matrix representation. And to find the cross product, I need to take the determinant. That's what these little bars mean in matrix multiplication in matrix math. This is the determinant of a 3 by 3 matrix. To find that, I write down my nice little I hat. And when I do that, I can cross out anything that's happening in the I hat column or row. Then I take a little fish. I draw a little fish, AY, BZ, AZ, BY. And that tells me how I'm going to multiply my variables together. I start with my AY. That's the beginning of my fish. So I write down my AY. Where does my fish go? My fish comes down to this BZ. So I multiply my AY times my BZ. And my little fish comes up, and I get to AZ. At this point, where my head flips over, where I'm going to the top of the fish, I need to subtract off this AZ. So I do minus an AZ. And then I finish off my fish at my tail, at my BY, and I multiply this AZ times BY. So what I've done here is I've used matrix math to figure out what components to multiply together to get me my cross product. They're going to be operating in the I hat direction, and it's going to be AY times BZ minus AZ times BY. Now I'm not done yet because I still have two different directions to go through. I have to go through the J hat direction and the K hat direction. So to continue taking the determinant of this, we need to take the J hat direction. So I cross out my column for J hat, cross out my row for J hat, I draw my little fish, and the important thing to note for this direction is that instead of adding, I subtract. So I subtract my fish that I make in my usual way, AX times BZ minus AZ times BX. And we can see this fish again, AX times BZ minus the upper part of the fish, AZ, all the way down to the bottom part of the tail, the BX. And that is going to be moving in the direction that I just crossed out, the J hat direction. This again should be a refresher from your previous math courses where you did determinants of 3 by 3 matrices. Now we need to do the K hat direction. And to do the K hat direction, we cross out our K column, we draw our fish, and our K column goes back to the normal way of choosing signs. So we have plus K hat direction times our fish. We started our AX, draw our fish to BY, and then subtract AY times BX. We have our AX times BY minus AY times BX. Again, that comes from drawing our little fish shape. And now we have the cross product of A cross B in all general cases. In the I hat direction times AY BZ minus AZ BY, and so on.